Hi guys, welcome to my new video on the backpropagation, neural networks backpropagation. So when you talk about the backpropagation, what do you mean by exactly? All that things I will try to cover in this video. I will cover how to train the neural networks, what is a backpropagation exactly, and the gradient descent. So this video will give you idea of these topics. What is a backpropagation? When you talk about the backpropagation, it may sound little bit new to you, but this is one of the things used in neural networks to adjust the weights. Now, what do you mean by weight? We will see. So errors are backpropagated in the layers of the neural network, right? And weights are getting updated. So gradient descent optimizes the functions by iteratively adjusting the parameters in the direction of the steepest descent. The statements might sound little difficult to you, but don't worry, we are going to see in detail what's the backpropagation, what's the gradient descent is. Well, this is our data set. X is 1.2 and desired output. So if I provide X value as input feature as 1.2, I'm expecting output as 0.7. So this is what the neural network we would be considering for this video. There would be only one input layer, output layer, one output layer, one weight is there. Input layer single node, output layer single node, and single weight is there. No bias is considered, okay, and no non-linearity is considered, which means that our activation function A, so if you see, X is called as input, W is called as weight, and the output is called as A activation function. Activation function is non-linear, which means that this is simply the product of input and the weight. That's it. Right, let's try to code this much part first. Let's go here and let's try to define X is equals to, let me connect this first. X is equals to 1.2. Okay. Y is the output or desired output 0.4, and we can say weight is equals to 0.1. Weight is equals to what? 0.1. So if you go here and see, this is X is 1.2, weight is 0.7. Then output activation A is equals to 1.2 into 0.7. So if you go here, weight is 0.7. Then output activation we need to calculate. Let me run this much code. And output activation A is equals to capital X into weight. Capital X into what? Weight. Now, if you try to print this A, you will see 0.84. That's what is this. This is nothing but what? 0.84. But desired output is 0.4 and you are getting output as 0.84. So what we are saying, desired output is 0.4 and you are getting output as 0.84. There is a difference, right? Now what I want to do, I want to change A to 0.4. I want to change A to what? 0.4. I want to change A, just a minute. Yeah, I want to change A to 0.4. So what things shall I change? Can you change X? Because A is equals to X into W. A is equals to what? X into W. So if you change X, definitely this output will change. But you cannot change X for the reason X is the input feature. It's kind of constant. So it is not allowed to change the X. So can you change A directly? No. A cannot be changed directly because it's a product of X and W. It's a product of X and W. So what can be changed over here? Only one thing can be changed over here, weight. So first you analyze, can I change A? No. Can I change X? No. So, and you are going back in the direction. Can you see you are going back in the direction and you are checking what exactly can be changed. This idea is called as back propagation. Going back and check what can I change. So definitely you can change only weight. So from this you can change, from this idea, whole idea, what you can change? You can change only W. And that's why W is called as trainable parameter. So our neural network has one trainable parameter. That is nothing but what this W. Now I want to change W in such a way that so from 0.84 it should come down to 0.4. This is the output. From 0.84 it should come down to 0.4. Now the difference between predicted output and the desired output is called as loss, cost or error. There is a difference. This is a predicted one and this is the actual or desired one. There is a difference. And in the maths, there are some techniques to calculate the difference. So one of the technique we are going to use in this video is mean squared error, MSE. What is MSE now? So this is the predicted. So difference is squared. Predicted minus actual and square of that. So this is the predicted, this is the actual. So difference between, so one of the mathematical function MSE, predicted minus actual and the squared. And if you plot the graph on the x-axis, you would be having the predicted or output activation on the x-axis. On the y-axis, you will having the loss, the actual loss you have got. And you will find that it's a parabola, right? And it's a parabola. Well, there is a meaning to this thing. There is actually meaning to this thing, right? So can you see the loss is maximum over here and loss is minimum at the point here. Loss is minimum at the point over here. This is the actual concept in the neural networks. So we'll talk about this shortly. But this is what the cost function. If you want to calculate the difference between predicted and actual, you need one of the mathematical function. There are a lot of things are there. RMSE there, MSE mean squared error, root mean squared error is also there, and other things are also there. Let's not talk about that. Let's keep it simple. Okay. Now, by considering this cost function, you need to update the weight. So first you need to calculate the loss, and according to loss, you need to update this weight. So what is our idea? What is our idea? How much loss changes if we make little change in the weight. So do not forget this thing. Do not forget this thing. Your output activation A is the product of input and the weight. So in here, you cannot change A directly. You cannot change X directly. Only one thing is changeable is W. So if I make a little change in W, how much this activation would be getting changed? If I make little change in W, how much activation would be getting changed, right? And this is what the updating weights. So how much loss changes? Loss again, output activation has been changed. So what is the loss? Try to understand over here. Loss is nothing but the difference between predicted and the actual. And that's why A matters over here. If you see, loss means what? This is the A in our case. This is the mathematical formula. In our case, this is the A minus Y square. So if weight changes, if you change the weight, A is going to be changed. If A is going to be changed, loss is going to be changed. So how much loss changes if we make little change in the weight? We need to calculate that only. And this is the actual problem of the neural network. That is minimizing the loss by updating the weights. How much loss changes if we make little change in the weight? It is the actual problem of the neural network, that is minimizing the loss by updating the weights. Now how to do that thing? So how to calculate that? If I make little change, how much loss would be getting changed? In other words, we need to find out rate of change of loss with respect to the weight. We need to find out what? Rate of change of loss with respect to weight. But how? And maths answer this question. Use derivatives. We need to find out what? Rate of change of loss with respect to weight. You need to figure out this thing. We have seen why. We have seen a lot of things in the theory. We need to find out rate of change of loss with respect to weight. And how to figure out this thing? Mathematics says that use derivatives. Derivative of loss with respect to weights. Okay, let's go here and let's go here and let's do this thing. So here print a x into weights, and now I need to calculate the cost or loss, whatever you can say. A minus y is desired output, A is your predicted output, and it's square. This is what the cost is. And if you can print this cost, here you will see your cost is something like this, right? Your A minus y square, your cost is something like this. Okay, so we have got the loss or cost, and we need to find out if I change this W, how much this cost changes. If I change this W, how much this cost changes. We need to identify that. Okay. Now, derivative of loss with respect to weights. But there is a problem. If you look at this equation, cost and weight, can you see this cost and this weight are not directly proportional or not directly associated. This cost, if you look at the equation over here, they are not directly associated. Indirectly they are associated. Cost and weight are not directly associated, right? So cost is a function of A. C of A is equals to A minus y bracket square, right? This is this equation we have written. Cost is equals to this equation we have written. Sorry. So cost is a function of A minus y. C of A is equals to A minus y bracket square. See, these are the mathematical terms, function and other thing. You don't need to worry about now. Just remember that cost is a function of A. Now you can go to the Google and search out what do you mean by functions and domains, right? You will get to know. That's easy. Now cost is a function of A, that is A minus y square. In turn, A is a function of W, right? Output activation, A is nothing but what? The output activation is a function of W, that is X into W. Which means that here we can see the cost is a function of A and A is a function of W. Means one function is the function of other function. f of x is equals to f dash of g of x. This is the scenario over here. Loss and weight are not directly associated. Here loss is a function of a and a is a function of w. Loss and weight are not directly associated. Here also you can see this is the cost and w, they are not directly associated, but cost is a function of a and a is a function of w by keeping x constant, right? So f of x, f dash of x, and so you cannot directly take the derivatives of these things. Derivative of loss with respect to weights cannot be taken directly because they are not directly associated, but they are indirectly associated in this manner. F of x is equals to f of g of x, f of g of x. So again math says that, boss, this is easy. If you want to take the derivative of something like this, loss and weight, they are not directly associated, but they are indirectly associated, which is nothing but this f of g of x. Math says that use the chain rule of the derivatives. What you need to use? The chain rule of the derivatives. So f of g of x. So this is the standard formula. Go to the Google and search out the standard formula for chain rule. You will get detailed explanation also for this chain rules, how they have come to this point, but you don't need to go in that deeper level. You just need to know the formula for the chain rule. And when chain rule is getting applied, if one function is a function of another, at that time chain rule is applied. And what is the standard formula? Whenever you need to take a derivative of this f with respect to x, g dash of x, g dash means this derivative can be represented in this form, or they can be represented in the dash, g dash of x, f dash of g. Can you see? G dash of x. So derivative of x with respect to the g, and derivative of g, this function with respect to g. So in our terms, derivative of loss with respect to weights, can be calculated by derivative of loss with respect to the output activation and derivative of output activation with respect to the weights. If you see here, this dA and this dA gets cancelled. They are cancelling over here. You can cancel this dA from here. You can cancel this dA. So what remains? Derivative of loss with respect to weights. Now let's try to understand these terms. What do you mean by derivative of loss with respect to A? So remember that as output activation changes, how much our loss is changing. Let us see they are associated or not. Yeah, can you see cost or nothing but the loss? If A changes, it is going to change the cost. That's what we need to calculate. Derivative of loss with respect to the output activation. So meaning of this symbol is that how much loss changes if we change the output activation. As this output activation changes, loss also changes. So we need to find out rate of change of loss with respect to A, and that can be calculated because this cost or loss and A are directly associated. Similarly, dA by d weights, which means that what? How much output activation changes if I make a little change in the weight. How much output activation changes if I make little change in the weights. That is, we need to find out rate of change of output activation with respect to the weight. Rate of change of output activation with respect to weight. How much? So when you say symbol like this, you can say that how much output activation changes if I make little change in weight. Let's see. Yeah, can you see this is the output activation A, and if you make little change in the weight, of course this A is going to be changed. Means this is related. So we can derivate this thing, we can derivate this thing. That's what, nothing but your chain rule. Derivative of loss with respect to weight. D loss by dA into dA by d weight. So if you cancel this dA, what remains? D loss by d weights. Right? This is a way of remembering this thing, but technically in the mathematical term, this is the chain rule. Okay, how do you calculate this D loss by dA? How do you calculate this D loss by dA? So what is the mathematical, how do you calculate this D loss by dA? Need to calculate the derivative of loss with respect to output activation, which means that if output activation changes, how much loss is going to be changed? Derivative is nothing but what? Rate of change of one thing with respect to another thing. That's the mathematical thing. In the calculus, we use this. So loss is equals to, what is the equation of the loss? Loss is equals to y dash minus y. And we need to take the derivative of this equation with respect to A. So y dash becomes A now. And here you need to apply the standard derivative rule called as power rule. A standard derivative rule called as power rule. So this 2 becomes over here into, so 2 becomes over here into 2 minus 1. That is the standard rule. N into n minus 1. So here n multiplied by this term and here n minus 1. That's the power rule is. So 2 into y dash minus y is equals to this. Okay. Now let's go here and let's try to first get the derivative of this. And here I can say dA by d, derivative of loss, by weight is equals to derivative of loss by weight. What's the formula? 2 into y dash minus y. Here y dash can be output activation. So here you can say 2 multiplied by A minus y. This is the formula, A minus y. This is the formula for D loss by D weight. Similarly, let's get the, I will come back to this slide shortly. Let's get to this dA by d weights. So here, so we have calculated this. We have calculated what? D loss by dA. Sorry, here D loss by, not weight actually, D loss by dA. We have calculated this term, D loss by dA. Now we will calculate this term, dA by d weights. That is nothing but this dA by d weights. We need to find out how much output activation change if we make little change in the weights. So what is the formula for A? X into W. What is the formula of A? X into W. Output activation is equals to X into W. So derivative of this equation can be taken from the derivative of the line, equation of line. In the equation of line, y is equals to mx plus c. In the equation of line, y is equal to mx plus c. So derivative of line is always the slope. So in this case, so we need to derivate by means of dA by dW, which means that x is the slope, and that's why dA by d weights is equals to x. Consider that this is the equation of line, a straight line which is passing through the origin as y intercept is missing. because we don't have a bias term over here. So if you draw the line of this, that will pass through the origin, right? And then here if you see, if you derivate this with, by considering this is the equation of line with respect to weights, dA by d weights, the equation, so answer is the slope, in this case x, and that's my answer over here is x. So let's do that thing also. D loss, now dA by d weights is equals to dA by d weight is equals to this x. X is nothing but what? The input feature. So A is equals to x into weight. Then we have taken a derivative of this, which is nothing but what? D loss by dA, this thing. Then we have taken a derivative of this, which is nothing but this. Now if you calculate D loss, now we are getting our full equation. D loss by d weight is equals to D loss by dA into dA by d weights. Let's go here and see D loss by d weights. D loss by d weight is equals to, let's not make a plural, let's make a singular. D loss by d weight is equals to dA by d weight into dA by d weight into d loss by dA. Can you see? dA by d loss by dA, right? This is our equation, is d loss by d weights is equals to, or derivative of loss with respect to weight is equals to derivative of loss with respect to output activation and derivative of output activation with respect to the weight. So derivative of output activation with respect to weight and derivative of loss with respect to output activation, right? Now if you just try to print these things, print D loss by dA, so you'll not get anything right now. If you try to do that, you'll not get absolutely anything. And print D loss by d weight, and here if you see, some values you are getting like this, but still we are not applying the rule. We are not applying the back propagation yet. If you want to understand the back propagation, one thing you need to know about this thing, right? Now, in which direction you need to update the weight? If you see, the derivative of loss with respect to output activation is a straight line, right? See this. So presently, because of values, the parabola is a little bit smaller. So this is the parabola. A same parabola is there, but because of the values, the curve is little bit smaller. But if you see, this is the loss function, and this is the slope of the line. So if you see this parabola, and this is the line which have been drawn, of this derivative d loss by dA, and that is nothing but the vertical line. So what this vertical line says that, what this line says that if you come down over here, you will reach to the minimum point. Can you see here? if you come down from here to here like this, you reach to this point where loss is minimum. In this case also, loss is minimum over here, right? At this point, loss is minimum. Now what we need to do, we need to travel from maximum loss to the minimum loss. But what's the problem? We need to know the direction. In which direction shall we come down? Shall we come down or shall we go up? Shall we come down or shall we go up? Right? If you see here if you see, you are going up. But here, if you see, from if you are standing at this point, and if you want to come down to the loss which is a minimum, you need to come down. So we need to plot one more line. We need to plot one more line over here which represents the slope. So we have taken a derivative of this parabola and then we have drawn this line, and this line says that if you come down, if you are here and if you come down on this line in this way, you will reach the minimum of the loss. If you are standing here, right, and you need to come down from here, you just need to slide from here on this line and you will get one point, and this point is the minimum. So what this line gives you, the direction where we need to change the weight. If you see the direction in which we need to change the weights, that is negative of the slope or negative of the gradient. So towards this slope is positive. Negative means what? You need to come down through this line, and at the certain point you will get, at that point your loss is minimum, right? And that weight would be your required weight. So slope of a loss represent direction in which, slope of the line which represents the direction in which we need to change the weight. That is a negative of the gradient. Gradient is nothing but what the slope is. Okay, so we have seen this point. Now one more thing is that adjustment. So while coming down, the magnitude by which we need to make the adjustment is called as learning rate. So you cannot directly come here and then go here, so you will miss this point. So can you see the magnitude by which you are going to change the weights? So I'm coming down. So first I need to come here, then here, then here, then here, then here, then here. So this magnitude by which you are adjusting the weights is called as learning rate. Bigger the value, you'll get one more concern, exploding gradients, and smaller the value is slow down the training process. So that should be moderate. That's what the learning rate is. Okay, now let's try to do this thing first. Now weight update is important. So how do you update the weight? Now see, I need to update the weight is equals to weight minus the learning rate. So we need to define the learning rate. Learning underscore rate is equals to 0.1. Let's run this. So weight minus learning rate into this your d loss by d weight. So if you want to update the weight, existing weight minus, you need to come down the learning rate. whatever learning rate you are giving, into d loss by d weight. Okay, so for better understanding purpose, I will comment all these print statements and we will just print whatever required things are. Right, now you are updating weight again and again. So here we can print loss is equals to cost. Then we can print weight is nothing but the weight, and then we need to print output activation. Output is nothing but what? A. Right, just run it again, run this again, run this again. Look at the loss is this, weight is this, and output 084 is this. Now we need to repeat this step again. We need to repeat this step, and this thing is called as training process. Just repeat this thing, and run the project. And here if you see, here loss is 0.098, weight is 0.51 whatever, and output is this. Output is output activation. At the second iteration, loss is this, weight is this, output is this. Third iteration, loss is this, weight is this, and output is this. See what is the desired output? 0.4. Can you see you are reaching to the, can you see you are reaching to the 0.4? Just add a few more iterations. You can write a for loop also, but for explanation purpose I'm not writing it. 3 more steps I have written. And can you see here, so loss is getting minimized. So here loss is 0.006 and here loss is 0.001. Loss is minimizing, weight is this, and can you see you are reaching towards what you can say, a desired output. If x is this, desired output is this, and initialized basic initial weight is this, but you made some iterations, that is called as a training process where weights are getting updated, and here you got something like this, right? A gradient descent, weight adjustment, learning rate, and back propagate the adjustments. So first we have seen slope of the cost functions, in which direction we need to update the weight. Learning rate decides the magnitude or the amount of adjustment that should be made, and adjustments are back propagated. Can you see here weight is getting updated per iteration, weight is getting updated, weight is getting updated, weight is getting updated. Back propagation, and this algorithm is called as gradient descent. What is a gradient descent? Reaching from this point, maximum of the loss, to the minimum. So this point is called as the point where loss is minimum, right? Now I have written few functions to plot these things. To plot these things. So I will just copy paste those functions. These are the matplotlib functions. So here you can plot the loss with respect to the activation function, right? Plot the loss with respect to activation function. Can you see over here this thing? And another function with respect to our data. Plot the loss with respect to weight. Plot the loss with respect to the weight. Now if you see here, same thing. So loss has been calculated in this way. Now if you analyze this graph, this is the parabola, this is the slope, and when you come down to the slope, and can you see the point? So on this axis we have weights, and on this axis we have losses, where here you have output activation over here and the losses over here, but graph is little bit changed. So here weight is there, we have the weights, and here we have the losses. So if you come down, so this is the parabola, a loss function curve, and this is the slope of the loss, which gives you the direction in which you need to come down. So from here you come down by means of learning rate, like this, like this, like this, like this, and here you reached. Can you see? If you see this point, weight, what's the expected weight over here? 0.3 or something, 3.1 or something, right? Which means that a loss is minimum at this value, some 0.3 or something. Can you see? Loss is 0 over here, loss is 0, and this point is 0.31. Now if you go to our code, output of the code, can you see? So desired output is 0.410, and can you see weight is 3.3, 0.33, and output is desired one. So if you go on iterating, just try to do that thing. Write this line, write this code 100 times now. It will not go beyond that point. Run it again, and can you see? Can you see? Weight a little from here your weight is at 0.33, right? Here weight is at 0.33 and loss is getting minimum. It's a e raised to, remember that, and you have reached the desired output 0.400, meaning that you have come down from this point to minimum of this thing, right? And this problem is called as gradient descent. And few outputs I have written over here: gradient descent, weight adjustment, learning rate, and the back propagation. So presently we have done this for one input and one output, but in actual neural networks there might be a lot of hidden layers in between, but analogy is same. The updated weight, you will pass it to the previous layer. That updated weight, you will pass it to the previous layer by derivating it. So I will cover that in some other video. But as far as the back propagation and the fundamentals are there, they remain same. Whatever we have discussed, they remain same. Well, I will give you a link of this notebook in the video description. Also, I will share these slides on the GitHub. Okay. If you have liked this video, if you have liked my content, please let me know in the comment section. Also, if you find it helpful, please do subscribe me. That motivates. Okay. Thank you. We'll meet again in next video. Thank you.